In this module, we're going to talk about clustering, which is another type of machine learning analysis which is focused on finding groupings in your data. And so today we're going to look at why we should do this. What are some of the potential uses of clustering? And we're going to introduce some more exploratory data analysis techniques, especially pairplots, which are basically a series of scatter plots that look at relationships between each pair of variables in your data. And we're going to then turn to k-means clustering, which will be the focus for the rest of this module after this lecture as well. So why should you cluster? Well, clustering helps you identify sensible groupings in a data set. So you don't know what these clusters are going in. There's no labeling that tell you what the correct cluster is. And that's a big difference from the types of classification problems we looked at in the last module, where we did know the correct answer. We did know whether there was, for example, an ADU on a particular plot of land. So that means that cluster analysis is called unsupervised learning. In other words, we don't know what the right answer is. So we can see some potential applications of clustering in our GitHub notebook. So Bohorquez and colleagues looked at different types of marine protected areas using a cluster analysis. In some of my own work with Chris Barrington-Lee, we use cluster analysis to identify different types of street network. So can we identify types that are grids versus cul-de-sac or dendritic street networks? Types of transit agencies, types of patterns for cruising, for parking. These are all examples in urban studies and urban planning where cluster analysis can help you understand patterns in your data. Formally, if you do a cluster analysis, you take a set of n objects, so n number of observations, and you find k groups. So k usually refers to the number of groups. And those groups are based on some measure of similarity. And if you want a more detailed, technical but still pretty accessible overview, I recommend this paper by Jane in 2010, Data Clustering 50 Years Beyond K-Means. And K-Means is really the standard cluster analysis algorithm, which we'll focus on here. That's not the only way to cluster. Some analyses use hierarchical algorithms. So this paper by Ederer, so you start off this hierarchy, and you have these two groups, one of which is LA Metro, and San Francisco, Chicago, Boston, and so on. And then this is the other group here. And then you go down one level of a hierarchy, and then you divide it into two further groups. And then so on and so on, until eventually there's only one transit agency in each group. So that's a hierarchy. You can, there's a natural relationship between these different clusters. But we're going to focus here on a partitional algorithm, which doesn't have this hierarchy. There's just clusters that don't have any particular relationship to each other. And again, the most popular here and the most commonly used for a good reason is called k-means. So the number of clusters is given by k, and basically you should experiment. Try different values of k until a sensible grouping emerges. What do I mean by sensible? Well, something that you can interpret and that you find useful, because the whole point of cluster analysis is to do something that you find useful. There's also another method to choose k, the elbow method. You can look at the link here, but we're not going to discuss that further in this lecture. So the example we're going to focus on uses voting data in California. And we're going to see if we can identify different clusters of precincts. So the underlying data comes from a California statewide database that's maintained by UC Berkeley. And there's a subset of that, the 2020 precinct data for LA County and the November 2020 election, which is in GitHub. So it looks like this. Right? We have some district numbers. So each row is a precinct. We have a total number of registered voters and those that are registered by different parties. and then voting on the different propositions. So, for example, Prop 24, the number voted yes or no in that precinct, and then Senate and other candidates as well. In this column here, SR preq, this is the unique identifier. So we're going to set that as the index. Again, in place equals true, so it modifies it in place rather than returning a new data frame. And let's check that this is a unique identifier. We'll confirm that df index, what's our index? Well, we just set it, and we get true, so that is unique. So there's a lot of columns here. We just saw some of these, and there's a full code book here. This is a very well documented data set. You can explore that. But most of these columns are pretty self-explanatory. For example, this pres-dem column here gives votes for the Democratic candidate in November 2020, which was Biden. Pres-rep 01 gives the number of votes for the Republican candidate in that precinct, and that was Trump. There's also state senate and assembly races. These are going to have different candidates depending on the precinct. In California, obviously, there's the same presidential candidate, but there's lots of different state and senate and state assembly candidates. So let's have a look at just a few of these columns, and we see that the numbers are in absolute terms. So the first step we want to do is convert these to vote share. So this is where I want you to pause the video and go about creating a column with the percentage vote share that Biden got versus Trump, so the two-party vote share. So how can we do that? Well, we know that this is the pres-dem 01, that's the absolute number of Democratic votes. And then we divide that by the total number of votes for these two candidates. We could include minor party candidates too, but let's keep this simple at the two-party vote share, and then multiply by 100 to convert to percentages. And let's do the same for each of these propositions as well. So here we're going to use a list comprehension to get the list of relevant columns. So what am I doing here? I'm going to loop over the list of columns in this data frame. And then I'm going to just return the unchanged column name and put it in a list. But what do these if ones do? Well, these are only going to return it if these two conditions are true. If the column name, if a string, if it starts with PR for proposition, and it ends with yes. So this is going to give us the list of votes that are in favor of each proposition. So how do we extract these numbers? So 14, 15, 16, 17. Well, we can use another list comprehension. We'll note that the numbers are always the fourth and fifth characters. So 1, 2, 3, 4, 5. So we can extract it with just a string indexing. Remember, 0 index, so 3 is actually the fourth character, and we want the next two characters. And then let's apply this in a list comprehension. So we'll loop over the props. So this is this list that we just got here. And let's extract the fourth and fifth characters, and then print it. And we could have done this all in one go. We could have combined this list comprehension and this list comprehension up here, and we should get exactly the same result, and in fact we do. So now we have a list of propositions. We can calculate the vote share for each of these. So let's loop over these. So let's basically loop over this list here. And for each one, we'll calculate a new column, which we're going to call the proposition number and %yes. And what is it? Well, it's the number that voted yes divided by the sum of the yes and no votes, and then multiplied by 100 to convert to percentages. And so that looks reasonable. We get numbers that are between 0 and 100 for each of these propositions. And notice we get nulls in some places where there's just, it looks like no one voted in this precinct. So before doing any cluster analysis, or for that matter, any data science algorithm to your data, look at it first. That will give you a sense if there's any problems, but also have a sense of like what might be some interesting patterns that you can analyze more formally. Well, we could create a scatter plot matrix manually. Right? We could create lots of different plots and we could loop over all our variables and do scatter plots. But Seaborn has a nice function to do this for us. It's called pairplot. So let's import Seaborn, and we see that we pass it the data. We can also optionally choose the x and the y variables to use. And so it creates a grid of axes so that you basically plot every variable against every other variable. And so there's some more detailed documentation there, but let's just try it. So first of all, let's just do a subset of the columns. So let's only plot the ones that have percentage. These are the ones we just calculated, right? So again, another list comprehension. We're going to loop over the columns in data frame, and we're only going to keep it and put it in this new list if this string is in the column name. And then let's remove a few of them. These are some of the less critical propositions that, in my view, like why are these on the ballot every couple of years? Why can't the legislator just decide? So we'll just remove these from the list manually. And then we'll call our pairplot. So the format here, just very simply, just a subset of the columns in the data frame that we want to plot. And then kind equals reg, short for regression. This is going to add a line of best fit to every cell. So we get these different bivariate plots. So notice x variables, or y variables here rather. So Biden, percentage, and percentage on all of the propositions are plotted against all the other ones. So here, for example, this cell, this is a percent voting for Biden against a percent voting yes on Prop 25. And then the diagonals, these are just the distributions. So for example, for Biden, you can see there's a pretty positive skew. Los Angeles is a Democratic county in most precincts, but there's some heavily Republican precincts down here. So we can see that California voters are pretty consistent in that there's a really strong correlation between pretty much all of these propositions. Right? If a precinct is more likely to vote for Biden, they're more likely to vote yes on this precinct, this one, this one, this one, this one, and then two that have a negative relationship. And these look like Prop 20 and Prop 22. Prop 20 is actually a proposition that was calling for harsher sentencing laws. Prop 22 was about independent contractor status for drivers for Uber, DoorDash, and other ride-hailing and gig economy transportation firms. You can look at what these propositions were at this link here. And so it's not surprising that voters seem to have relatively consistent ideological positions. If you are voting for Biden, you're less likely to vote for harsher sentencing in criminal cases. But notice that there isn't a deterministic relationship. Right? There's a correlation, but not all of the precincts are lined up exactly on this line of best fit. So perhaps we think that cluster analysis can reveal some different groupings. Perhaps there's precincts that are oriented towards the Democratic candidate for president, but have different views on, say, sentencing or on any of these other issues that are raised in the propositions. So let's use some cluster analysis here. First of all, let's pre-process the data in two ways. First of all, let's align the data so that a higher percentage means more progressive. So that means basically flipping these two propositions where there are negative correlations. So we're looking at the percent no rather than percent yes. And secondly, let's standardize each variable to mean 0 and standard deviation 1. We did this with the neural networks. And technically this means that the distances in this multi-dimensional space, so you have one dimension for each of these propositions, it makes sure that they're consistent. So you're not giving more weight to a variable, for example, because it's measured in millimeters compared to a variable that's measured in kilometers. How do we do this? Well, for these two propositions, let's just calculate the proposition no, 100 minus the percent yes, and then drop the percent yes column. And then in place means that we do that, we modify the data frame rather than returning a new one. And now let's rerun the same code as before. Let's create our list of columns, all of the ones that have percentage in the name. Let's remove the ones that we don't want to plot. And then let's use a standard scaler in the same way as we did before to return a scaled version of the data frame that is normalized to mean 0 and standard deviation 1. And I want you to pause the video here and look at the details of some of these objects. So what is this scalar object that is returned? Like, what can you do with it? What does this scalar transform do? Here we just put it directly into a data frame, but what happens if you just look at it on its own before we put it into a data frame? What can you do with this type of object? So let's move on and check that our data still look reasonable. So we can rerun exactly the same pairplot, just with our standardized data, so df scaled, rather than our untransformed data. So it looks like we got exactly the same result in terms of we have these correlations between these variables, but notice that the scale here is roughly from -3 to +3 on both the y-axis and the x-axis. So this is what our standard deviation does. Like, everything should have mean 0 and standard deviation of 1. So most of your observations are going to be between -3 and +3. Okay, so now we've done our data wrangling. As always, that's a large part of your data science workflow. So now we can do the cluster analysis, which, as with a lot of these types of techniques, most of the work is in preparing your data. Cluster analysis is just a couple of lines of code. So we're going to use the k-means function from the scikit-learn library. And it has a pretty simple syntax that you just specify your number of clusters. What does star mean? Well, let's look at some of the examples here. So it looks like that you initialize a k-means object just with a number of clusters and some other of these hyperparameters, and then you fit it to your data. We can also specify the random state, and remember that means that we can reproduce our work. There's a little randomness in these algorithms, but if you specify this random state parameter, then that randomness goes away. Okay, we get an error here. What's happening? Let's see if we can figure out what's going on. Well, here it's a pretty simple and helpful error message, right? Input X contains NaNs, so missing data. Some algorithms deal with missing data, some don't. Here we just have to do it manually. So let's look at the length of our data frame. Before, let's drop the NAs, print the length again, and then refit it. So it seems that we had about 1,000 or so precincts with missing data. Many of these precincts, they just don't have any voters, or maybe no one voted on one of the propositions. And here we get a future warning. This here is kind of deep in the depths of the package. This is basically for the developer of this package to know that one of their dependencies has changed. So we have this k-means object. Tells us we have 5 clusters and a random state of 1. Well, what can we do with it? Well, let's use tab autocomplete to see what are some of the attributes and functions. Well, we can look at the cluster centers, perhaps. That sounds useful. We can look at the feature names. We can look at the labels, the number of clusters. Well, we know that. We told it was 5. And so there's some other attributes that you can explore on your own. So what are cluster centers? Well, these are defined by the standardized value for each variable. So remember, standardized value just means it's on a -3 to 3 scale with a mean of 0. So it looks like we have a list of lists, or an array of lists that's similar to a list of lists. We know that by the double square bracket here. So we have, looks like a 10 by 5 array here. Why is it 10 by 5? Let's confirm this just by looking at the shape here. Yep, so, or 5 by 10. So why is this? Well, we asked it for 5 clusters, so it's not surprising one of these dimensions is 5. And we also had 10 columns. So we had 10 variables that we're using to define these clusters. So each cluster is defined by the center in terms of its value on each of these variables. So for this cluster, it's minus 0.398, minus 0.49, and so on, a value for the center on each of these 10 variables or columns or propositions. The other attribute that might be interesting is labels. So this gives us the identity of the cluster to which each observation is assigned. So our first observation is in cluster 2. Our second observation is also in, and our third observation is also in cluster 2. And so our shape of this, so there's as many labels. So we have 3,082 labels, and that's, fortunately, it's the length of our data frame. So each precinct or row in our data frame is now assigned to a cluster. So we can simply add the label back as a new column to our data frame. How large is each cluster? Well, let's look at the sizes. You're just using the group by cluster ID. This is a new column we added, and what's the size? So notice that the algorithm isn't trying to produce equal size groupings here. We have one really small cluster, cluster 3. There's only 32 precincts that fall into this cluster. The others are much larger. And so the point of the algorithm is to produce coherent groupings. They don't have to be the same size. We'll pause it there, and we'll pick up in the next lecture and see if we can visualize clusters and do some more exploration of what these clusters mean. But the messages I want to leave you with are, first of all, this is an exploratory data analysis tool. So there's no right answer here. The right answer, rather, is what you find helpful. And this is an example of data reduction. So in this instance, we had votes on 10 propositions. It's hard to get that straight in your head, like, hey, what are the types of clusters? You're trying to juggle all of these in your head. Cluster analysis reduces the number of dimensions from 10 to 1. So it's something that your brain can more easily interpret and hopefully is helpful in your future analysis.